welcome to the second lecture of heat conduction. So today we will go into the basics we need for simulating the temperature distribution in solid. This will be Fourier's law to start with, then the derivation of the heat equation, the finite element formulation of the heat equation. And finally, we will look at which kind of, how the discretized system looks like, which analysis types we can use for simulating heat conduction, and what type of finite element results we will obtain. Okay, let's get right into it. Fourier's, what is heat conduction to start with? We're dealing with thermal conduction. That means energy transfer by interaction of particles. So it can be molecules, atoms, or electrons. And this takes place in solids, liquids, and gases. And we know that the energy flux depends on the temperature difference between different locations, and the energy flows usually or always from higher to lower temperature. I also want to highlight what thermal conduction is not. So thermal conduction is not convective or advective heat transport. So if we transport heat by transporting material itself, this is not thermal conduction, and it's also not heat transfer by radiation. Okay, so how can we describe thermal conduction? The description is given by Fourier's law that is stated here in equation 7. We have the heat flux Q, or precisely the heat flux density, that is related to the temperature, and not to the temperature directly, but to the gradient of the temperature. And this relation can be defined by the thermal conductivity tensor K. Also note that the minus sign makes the heat flow in the correct direction, so that the heat flux vector always points from higher to lower temperatures. And to highlight the units we have in the quantities, temperature is in Kelvin usually, or in SI units of Kelvin. The thermal conductivity tensor is given in watt per meter per Kelvin, and the heat flux is given by watt in watt per square meter. So let's look at this in 1D. You probably have seen this example. The Fourier's law in 1D, we consider a wall here depicted on the left. We have a cross-sectional area of A. We have a thickness of delta X, and we know the temperature on the left-hand side and on the right-hand side. Then we can compute the heat flux density if we know the thermal conductivity K of the wall. So the heat flux density is then simply given by minus K delta T over delta X. And this can be written out and computed. So if we have the heat flux density, we can of course compute the complete heat flux through this wall by multiplying it with the area. And this term that arises here is the thermal transmittance that is often used for example, data sheets in isolation materials. So this was a 1D formulation. However, you've seen beforehand in the equation on the previous slide that the heat flux, the thermal conductivity is in general a tensor. And in the next example, I want to highlight why this is the case. So let's consider an anisotropic material. The material is layered, as you can see here on the left-hand side in the sketch. We have two materials that are layered on top of each other. And let's imagine this is just a unit cell, and this material repeats for a large area like this. And now let's imagine one component is a perfect isolator. So K1 is 0. There can't be any heat conducted in X direction since it's perfectly isolated by K1. However, considering the y direction, we can have heat flux in these layers of the material with K2. So this means the composed homogenized material behavior has to be direction dependent, meaning anisotropic. Therefore, the heat conductivity in general is a tensor that can incorporate the direction dependence between the gradient of the temperature and the resulting heat flux vector. Okay, so what we need for deriving the heat equation is conservation of energy. And I want to start with a simple 1D example. So from the first law of thermodynamics, the change of inner energy equals the production term and the work done on the control volume. We can write the energy balance. And if we write down the heat supplied to the system during a time t, we have first a production term. So we have heat produced in the material. And we can also determine the heat flux leaving or entering the control volume on the left boundary. So this would be at the location X. Of course, we have to multiply the heat flux by the cross-sectional area, so delta Y, delta Z, and by the time, delta T. And at the location of X plus delta X, we have heat flux leaving the control volume, and this is written here equivalently. Also note that the work done by the system is 0 in this case, so W is 0, and then we can also write down the change of internal energy due to the temperature difference over this time interval, so delta T, and this is simply given by the density and the heat capacity Cm of the material. So writing this equation down and dividing by the control volume size, delta X, delta Y, delta Z, we obtain the following equation where you can already clearly recognize the differential quotients here. So this will be the time derivative of the temperature, and here this is the spatial derivative of the heat flux with respect to the coordinate X. And here we have the specific production term. So let's extend this formulation into 3D. Just to note, the mass density, of course, is given in kilograms per cubic meter, and the volumetric heat capacity is given in joule per kilogram per Kelvin. So let's extend this conservation of energy in the general 3D framework. It follows directly from 1D, so you can write down the 1D equation for the 3 directions, and what you get is the following continuity equation for internal energy, which describes the temperature change over time due to heat sources and sinks in the material. So the heat sources and sinks are the Q dots. The heat flux is the Q. This is a heat flux vector. And the internal energy, to remind you, is rho CmT. So this is a general continuity equation which relates the rate of change of the conserved quantity. So we want to conserve internal energy here to the divergence of the flux quantity. So our flux is our heat flux density here, and possibly sources or sinks of the quantity. So this is the Q dot here on the right hand side. Of course, the conservation of energy can also written in integral form using the divergence theorem. then you directly get the change of the temporal change of the internal energy is equal to the boundary integral over the closed surface of the flux quantity and the total production quantity. So the total production quantity is simply the volume integral over the source density Q dot, and the inner energy, again, the total inner energy is the volume integral over the volume internal energy. Okay, so let's look at the heat equation. We consider the conservation of energy and assume heat flux by thermal conduction only. So this is Fourier's law, and we can simply insert now the Fourier's law in our conservation equation and consider a constant isotropic thermal conductivity. This is why we can write it as a scalar K here. And we can also assume that our density and heat capacity are constant over time, so we can pull them out of the time derivative. And we arrive here at equation 9, which is our heat equation we will have to solve with the finite element method. What we have neglected in this formulation is convection. We have neglected radiation heat transfer, and we have neglected possible phase changes in the material which might produce or consume energy. Again, here the units are given, so you can make sure you have consistent units in the equation. And just to note that our heat equation is a special case of the convection diffusion equation. However, we have not considered any convective part, only the diffusive part is included in our heat equation here. So how do we obtain the weak form to obtain the finite element formulation? As usual, we have a few steps. The first step is to introduce a test function. Note that here we have a time-dependent problem. Nevertheless, the test function is never time-dependent. It's always constant over time. Then we multiply our PDE with the test function, integrate over the domain, apply the divergence theorem, and finally, we have to incorporate the boundary conditions. So this is very similar to the finite, this is the finite element procedure we have studied in the last lecture, and we'll now apply it to the heat equation. So let's start with the first step, multiply the equation with the test function and integrate over the whole domain. So this is what we obtain. The test function is put in front. We put the integrals over everything. So this was an easy step. The second step, or just as a side note, for the sake of brevity, I will neglect all the spatial and temporal dependencies, just to make the writing a little bit shorter. In the following, I've put them explicitly here that you see what is dependent on space and time in which manner. So the next step is to use the product rule to rewrite the second term here. So what we would like to apply the divergence theorem is, again, a divergence of a product, so a scalar times a vector quantity. And if we form this divergence, we get this expression, so gradient of the scalar quantity in the vector quantity times the scalar quantity times the divergence of the vector quantity. So this is our product rule. We can rewrite the term and then directly apply the divergence theorem to the divergence term, which will convert it into our surface integral over the closed boundary here. So this is what we obtain. The other terms we didn't have in the previous formulation derivation is the right-hand side term, where we simply have a test function time our known production term, and the other terms are standard. Okay, so what we still have to do now is the fourth step is to insert our material law. We have done this previously, and this was simply Fourier's law. We can insert it here for the heat flux. Note that we have only inserted here in the volume term, since at the boundary term here we still want to incorporate the boundary conditions which will be related to the heat flux over the boundary. But here we can recognize again our stiffness term, which has the gradient of the test function and the gradient of the unknown T involved. So the final step will be to incorporate the boundary condition. Just to a short excursion of what types of boundary condition we can have in the heat equation. So the simplest boundary condition is the Dirichlet type, specifying the temperature directly on the boundary. So this is known temperature. We know how we handle Dirichlet boundary conditions simply by not testing at the boundary location. The next term is the heat flux across the boundary. This can be either known, so Qn, or it can be 0 on gamma 0. So this is a Dirichlet type. This is a Neumann type condition, and either it is homogeneous or inhomogeneous. The last, or the almost last boundary condition is a heat transfer boundary condition. You've probably seen the equation here. We have the normal heat flux across the boundary equal to alpha times the temperature difference of the boundary with respective reference temperature. For example, the temperature of a medium flowing over the boundary. Then there are certain tables. You can look up the heat transfer coefficient for two materials. This gives you enough information to apply this heat transfer condition. And finally, we would have thermal radiation. Note that we do not consider thermal radiation within the material, but we can consider thermal radiation over the boundary to the remaining space. And we know this from the radiation law. We know that the heat flux is equal to sigma times the fourth power of the temperature of the boundary. Okay, so these are our four boundary conditions. Let's put them in our formulation. What we have to do is we have to split the boundary, the total boundary, in the different regions we have discussed now, and insert the boundary condition there. The homogeneous Neumann condition results in a 0 term, so this is why it's not included here. Again, and the Dirichlet condition also results in a 0 term because we don't test there. We assume the test function is 0. So we have the remaining 3 terms: the Neumann boundary condition, where we know the heat flux, the heat transfer condition, and the thermal radiation condition, where we have the fourth power of the temperature. Note that this is a non-linearity, and however, this thermal radiation is usually only necessary if we're dealing with very high temperatures. So for small temperatures, in many technical applications, you can neglect thermal radiation. Also note that the homogeneous Neumann boundary condition is the natural boundary condition. So this is direct, it's always applied by the finite element method if you don't specify anything. That means no heat flux across the boundary, which implies a perfect thermal isolation. A last note on the heat transfer. As you can see, we have the unknown still involved in the boundary term. So this means we have to assemble this boundary term into the system matrix, and not only on the right-hand side. So the term related to the known quantity, TR, the reference temperature, will be assembled to the right-hand side, and the other term has to be assembled into the system matrix. So with the boundary condition, we can simply insert them in our equation and obtain the weak form of the heat equation. So given an initial temperature field, we have a time-dependent problem. Remember, we have to know the initial temperature field at T0. And so given this temperature field, we want to find the time evolution of the temperature field in space and time such that our weak equation is fulfilled for all test functions T prime. So this is the formulation. And now let's see how our discretized system will look like. How do we obtain the discretized form? We use standard nodal finite elements for the discretization. We approximate test functions and unknown functions by our ansatz functions and unknown coefficients. So this is equal to the formulation that we've done before. And we apply a Galerkin procedure to obtain the discretized system. So how will this discretized system look like? If we have assembled the final system, we will have a capacity matrix C, we will have a stiffness matrix K, we have a vector of unknown that I denote X again here. So this is not the spatial coordinate anymore. Be careful, this is a little bit inconsistent, but however it should be recognizable. So our unknown vector X contains all the nodal temperatures here. And on the right hand side, we have a forcing vector. Okay, so this is our discretized system. It is a system of ordinary differential equations. As you can see, we have the time derivative of our unknowns here. And now let's look a little bit in detail how the components of the system matrices look like. I've given here the element system matrices. So for the capacitance matrix C, we have products of the ansatz functions. And for the stiffness matrix, we have the derivatives of the ansatz functions and the material parameter K inside. And as I mentioned here, the boundary term from the radiation condition, if we should have one. So as usual, the global matrices are built from the element matrices in the usual assembly process. What you can also see is that all matrices are symmetric. So Kij is Kji. And another side note is that the capacity matrix C in heat conduction is often denoted M due to its similarity with the mass matrix for mechanics, where no derivatives of shape functions are involved, whereas in the stiffness matrix K, we have derivatives of the shape functions involved. How do the entries of the forcing vector look like? Quite similarly to our weak form, not surprisingly. So again, we have ansatz functions and the known quantity, which we have to assemble over the respective boundaries. Also note that the forcing vectors can have contributions from all our boundary terms. So this is the heat source density, the heat flux across the boundary, and the reference temperature in case of heat transfer boundary condition. And of course, this forcing vector will always only have contributions at the locations or at the nodes where we supply boundary conditions. Okay, so we've seen this is a time-dependent problem. It's an ordinary differential equation. So this ordinary differential equation has to be numerically integrated in time for an initial condition x0 and the known forcing vector f of t. And this can be done by, for example, subdividing the time interval So we split our time interval from 0 to capital T into m equal intervals. So we assume a constant interval size and will apply a forwards time difference scheme. So we approximate the time difference, the time derivative by the difference quotient between the solution at t at time point n plus 1 and the solution x at time point tn over the constant time difference delta t. To abbreviate this formulation a little bit, we simply write the lower index n plus 1 to denote evaluation at time n plus 1. The last step we need is to decide at which point in time we evaluate k times x of t and our forcing vector. And then we have, when we have decided that, we can solve the resulting equation system for the unknown at the new time step xn plus 1. So there are a few choices that you can do to derive a time integration scheme. You can obtain different schemes depending on your choice. To evaluate our quantities, our time-dependent quantities, it's useful to use a convex linear combination between the respective time points n and n plus 1. And this is done here. So for our k times x term, we have evaluated it once at xn plus 1 and at point x, and we weight this by the integration parameter gamma p that we have introduced here. So we have gamma p here and 1 minus gamma p here. So the integration parameters between 0 and 1 usually. And we do the same for the right-hand side forcing term. And now you can rearrange these terms to obtain an expression for a linear system for the unknown xn plus 1. So what you've obtained is an effective system matrix C star here times our unknown vector, and on the right-hand side a loading vector, which depends on the properties of the known time step xn and on the forcing, the non-forcing at time point n and n plus 1. So in each time step we need to solve a linear system. And in fact, this integration parameter determines the integration scheme. So we have different integration schemes. You might have heard them already. We have the forward difference scheme or forward Euler scheme if we set gamma p equals 0. So this is an explicit scheme because it only takes into account the previous time step. An implicit scheme is obtained for gamma p greater than 0, and there are two important implicit schemes. The first is the trapezoidal rule, or the Crank-Nicholson scheme, that is obtained by setting gamma p 0.5. This is the second order accurate scheme for this equation. And you can also go to the other limit, the backward difference or backward Euler scheme that you obtain if you set gamma p equal to 1. So the last thing we need is which time discretization should we actually choose. And there are a few guidelines to choose a correct time step. First, explicit algorithms usually become unstable if a critical time step is exceeded. So basically, we don't want to use an explicit algorithm for, it can be shown that for the heat equation, for gamma p greater than 0.5, the algorithm is unconditionally stable. So this is very, very useful. However, this only applies to linear problems and linear elements. Also, an important note is that having a stable scheme doesn't mean that we get accurate results. It only means that we don't diverge to basically random vectors. So even having a stable scheme and you using too large time steps will give you inaccurate result, which leads to the rule of thumb to use for the heat equation. And this is typically related to the frequency of the excitation. So from the right-hand side forcing vector, for example, and you want to perform 20 time steps per smallest time period that is present in your excitation signal. This is a good rule of thumb that can be applied to the heat equation. And finally, we have the stationary or steady state case. So for constant time-independent forcing vector, the solution will reach a steady state over time. So the time derivative will tend to zero if the time goes to infinity. This means we can directly compute the steady state solution by simply solving the system Kx equals F, where K is our previously defined stiffness matrix for the heat equation, and F is our constant forcing vector. So in this way, we directly obtain the steady state solution in a static analysis. So finally, I want to give you a bit of overview of types of finite element results. So first we can classify them in this way. For example, we have primary results, which correspond to the degrees of freedom in the algebraic system. So for the heat equation, this would be the temperatures. Then we have derived results, which are computed from the primary result by using the basis function, usually via using differential operator. For our case, in the heat equation, this would be the heat flux density, which involves the derivatives, so the gradient of the primary results. And since the basis functions are defined locally on each element, derived results are typically evaluated within the elements and not on the nodal points, since there you have results from the corners of different elements and you would have to average them, for example. And then there are integrated results, which are computed by integrating a certain quantity over a region. The region could be a surface region or could be a volume region. An example for the heat equation would be the total thermal energy. We can also distinguish in another way. We can distinguish between field results, which are defined in the computational domain as a function of position, and history results, which are defined for a single point or region as a function of time. So what do we have in our heat equation? I've said already, the temperature is our primary result defined on the nodes. Then we have our derived result, the heat flux density, defined as the gradient of the temperature field times the thermal conductivity tensor, which is evaluated inside the elements, and the heat flux, which can be computed, for example, over a boundary gamma by integrating the heat flux density over this boundary.